But without further ado, I'm going to hand you over to Sina Siadat for his talk. Over to you.
Hi, my name is Sina Siadat, and I'm a software engineer at Yelp. And the title of this talk is Building a Small Language with Go for Fun. So let's do a few quick show of hands. How many of you have built an interpreter or a compiler? Cool. And how many of you have, what else can I ask? How many of you have had an idea for building a new language, whether you have built it or not? Okay, cool. In this talk, let me go back a little bit to talk about my motivation. So recently I've been interested in programming languages and type systems, and I've been learning languages like OCaml and TypeScript, and because the ideas in those languages are interesting. And for instance, I tried to bring some of those ideas to Go as well, like the sum type, the union type in other languages. And so I built a static analyzer for the empty interface in one of my previous talks. But building a static analyzer that works with that enforces some constraints on empty interfaces was crossing the boundaries of the language. So I thought, why not build a new language from scratch? And so this is the motivation for why I went to this route of building a language. And so in this talk, I'm going to go through the process of building a small language that could look like this, almost from scratch, using Go, the tools that Go provides for us. So in this language, it's a very small language. It just has functions, and there's a function for greeting, and there's a main function, just like Go. It's kind of like Go programs, but it's intentionally a bit different. So instead of curly brackets, we have begin and end, and instead of function, we have func. And so we're going to, what we're going to do now is to parse this code. And so the code itself is just a string of text, and we're going to write this parser in the middle to convert it into an abstract syntax tree. So just as a reminder, so that we know what we're talking about, this is an example of an abstract syntax tree. So if we're giving the code on the left 3 plus 2, this is an expression. And if we give it to a parser, the resulting abstract tree could look like the tree on the right. So it's a plus. The plus has two. The plus is a binary expression that has two children. One is 3 and one is 2. And so actually the Go parser, in the standard library, the Go/parser produces AST nodes that are defined in that package, Go/AST. And so this expression on the left is parsed as the tree on the right. And I can show that in code as well. So if we go to example, let me see. So the standard library provides this useful function, parse expression, that whatever Go expression you pass to it as a string, it returns an AST node, AST expression node, and we could print that out to see what it looks like. So the 3 + 2 expression was parsed, and this is the resulting AST tree, the AST. So moving on, sorry about that. Okay, I've done that. So now what we want to do in this talk is to write a program that when we give it the string on the left, it produces some AST, some tree that represents our program. And so after that, we could run that program, or that AST. So usually the compilers generate machine code, given a string of code, generate machine code like assembly code or maybe even C code. But the important idea I want to put across in this talk, I mean, if there's only one takeaway in this talk, it should be this, that we could generate abstract syntax trees, Go abstract syntax trees, and we could then do all kinds of cool stuff with Go abstract syntax trees. So if we convert our program to Go abstract syntax trees, then we would be able to use the Go type checker. We would be able to use, we would be able to print Go programs. We would be able to manipulate the AST using the tools in the standard library and in the X packages, in the tools repository. Yeah. So first, we need to tokenize our code. And to do that, we need a scanner. And another good thing about Go is that it provides a package for scanning code as well. So I'll show that in a minute. After we tokenize our code, so in this example, the fn is 1 token, then followed by greet, followed by open parentheses, etc. After we have tokenized the code, we give this series of tokens to a parser, and that parser will construct a tree for us, which in our case will be a Go AST. So this is the whole picture. There is string text here. The scanner converts it into a list or a series of tokens, and the parser transforms it into a AST. So just to demo the scanner, the green bits, the green sections. Let's go to this example. So this is the code that I had written in the slides. And we are giving it as a string to the scanner. So the scanner is in the standard library, and it can scan any text that is using the token. The tokens that it produces are like Go source tokens. So for instance, it can recognize integers, floats, strings, idents, and things like that. So with just a few lines of code using the standard library, we will be able to tokenize that code. And if I run this program, so this is just one file, and if I run it, so this is the these are the tokens that it has generated for our program. So we are one step, we have progressed one step. And now let's write the parser. So the parser is just a series of the parser in our case, in this presentation, is a handwritten parser. I'd like to think of it just as a series of ifs and switch cases and for loops. It's very, very simple. So, in this parser, these are just a few helper functions like skipping new lines, and the output of this function, the parse file function, is an AST file which is defined in the standard library. So AST file is a AST representation of a Go file. So basically, our parser is given a string and returning a Go AST. And the way we are doing is just we are going through the output of the scanner that we saw earlier, and we are just doing some for loops. Like here, I'm saying that if the inputs, the tokens have not finished yet, then continue doing the for, and check the current token, the literal current token. If it's a variable definition, if it's an import, it's a function. So in our case, in our program, it starts with an fn. So this case will be true, and we will just follow this function for parsing function declarations. And these are just a series of very basic ifs and for loops and switch cases, and very simple processing of the input stream, the token stream. Okay, so one advantage, let me just run this code as well, the parser, before moving on. So the result for parsing our code, this is again the tokens that have been produced, and this is the AST, the Go AST that has been generated for our program. And so our code has two declarations. So these two map into two function declarations in Go. And in the generated AST, we see two declarations as well. So this is the first one, and below that is the second one. So here this one is the importing of the font package, and this is the first function declaration for greet, and below that should be the function declaration for main. So this AST can be printed like normal Go code, as we see here. Again, this is something that the standard library provides, the AST.print function. You give it an AST, and it prints it as a valid Go code. And another, now that we have a Go AST for our program, we are able to do type checking on the AST as well. So if in our program we pass in an integer to a printf, it will return a compile time error because printf's first argument must be a string, the format string. So this is the advantage of one of the advantages that the generating a Go AST gives us. And because type checking is very complicated, and the Go/types package in the standard library that we can use for type checking any Go program is one of the largest packages in the standard library. The third one I checked last night, and so reusing, being able to use this great tool is really cool. Instead of writing our own type checker from scratch, because a type checker does all kinds. I mean, there's a talk by Alan Donovan about the type checker in Go, and it's pretty complicated. And I tried to write a type checker in like a week, but I decided not to, and so I decided to generate valid Go code, Go AST code, and use the type checker that's already available in the standard library. And one other cool thing that we can do is that we could actually invent new types in our new programming language that are not available in the Go AST, or and the type checker of Go is not aware of. So for instance, if we invent a union type on the left and we parse it as something on the right, so on the left side is not Go, is just new. The right side is just normal Go. So if we generate the AST for the code on the right, we will be able to use that file interface like a normal type in Go, and the type checker will analyze our code and produce compile time errors for us if we use it incorrectly. And we could enforce additional constraints on that interface if we could add some kind of annotation for us. So the information about this file type is contained in a kind of a generated private, maybe hacky file struct. But when we produce the AST for the code on the right, we are able to write static analyzers in Go that checks if we have used that type correctly. Yep, and so I can demo this one as well. So if I let's see. Okay, so here I have a just arbitrary syntax I've used for defining a new type called union, and using the parser, using those very simple if statements and for loops and switch cases, we go through these tokens one by one, and we generate an AST that looks like this. Let me just do it. It should work. No, it doesn't work. So the AST it generates is again just like the one below it. And so the main point of what I wanted to present in this talk is that with the AST, with the Go AST, we could do a lot of powerful things. The Go AST was intended to be used for representing Go code, for parsing Go and representing their AST. But what I am suggesting here is that we could represent other languages using the Go's AST, and then we could take advantage of all the cool stuff and the cool packages and tools that are available in the standard library for working with Go ASTs. Like writing static analyzers for them, running the Go type checker on them, and printing them as normal Go code and then compiling them into binaries. So yeah, that's the main idea. Thank you. Thanks. Questions? Happy to answer.
Can you combine your parser and can you have it so 90% of your language is standard Go, and 10% is custom? So you can extend the language and your parser knows to use custom or Go.
Okay, good question. So the parser in the Go standard library provides a few helper functions like parse expression, which I showed as well. So you could parse some parts of your code that you know are expressions or Go expressions using the parser.parseExpression function. But for instance, if you have a statement, even that can be done. I mean, if you have a statement, a Go statement, you could wrap it inside a function. And then that becomes an expression in Go, and then you could pass it to that. You could do these kinds of stuff, but one thing about the Go parser is that it's written with the assumption that we are giving it a specific AST, the Go AST itself. So you cannot use it for, if your AST is a bit different, you won't be able to pass it to the parser. This is what I have found. Yeah, or you could mark your code, your new language. For instance, you could add 3 dashes and say that everything above this line is normal Go code. Just parse it as a normal Go code, and everything below it is my own language. And then you could do all sort of crazy stuff with that. You can invent new types that interact with your Go code as well.
Hi there. Hi there, very interesting talk, thank you.
Thank you.
I just wanted to know what you thought, using the Go AST parser, how does that limit the language you can parse? Could you parse a language like Python, let's say, which was space indented?
So parsing Python would, first of all, we need to scan the code, tokenize it. And for that, we could either use the scanner in the standard library, because maybe there are some tokens in Python that are not in Go. I can't think of any at the moment, but there might be. But using the Go parser, I don't think you can do that for parsing Python. But you could use parser generators, like Yak and Leg, and the important thing is that after parsing, the thing that you produce could be a Go AST. I mean, even if you parse your Python either by handwritten parser or by some grammars or EBNF or I don't know any tool. If you could produce AST, Go AST after that, then you're good to go. You are able to represent Python code with Go AST as well. I think you can, yeah. And you could, that would mean that you would be able to do some static type checking as well on it, which might not be available on Python. I haven't used Python for a long time. But you could add constraints. I mean, you will have a Go AST, and if your types represent, the types in Python are represented well in Go, then you will have automatic type checking. And if you want additional type checking, you will be able to just write a static analyzer, and you could do that, yeah.
Is it possible to accidentally build like an invalid AST that you feed in to the parser? And if so, like what happens when you do that?
Okay, so if you write an invalid AST, good question. So you can actually, the Go/AST package defines several nodes. And for instance, a node for expressions, a node for switch cases, a node for if statements, a node for struct types. You could invent a new node, like a node for union sum types, stuff like that. And the structural, you will have a valid AST, but you won't be able to pass it to the tools that are available for Go ASTs, because they are usually written in like switch cases. If it's a expression, do that. If it's a struct, do that. And they will panic probably if they see some type that they don't understand, like a union type. But what you could do is that you could generate. You're not limited to one AST. I mean, you could have a few lines of your own language, and then the AST that is produced could be like could contain a lot of meta information that you need for doing your work. I mean, it doesn't need to be limited to one-to-one types. So if I create a union type, I'm free to like create like 3 structs that I need for each union. I'm sorry, my hand is so you will have the information, the raw information you need for that type in valid Go AST. Yeah. So yeah. So. You can, I think you can represent your programs even if they are not representable in Go. You can represent them using several structs and several, I don't know, meta information in Go. Yeah. Okay.
Did you run your sample program?
Say again.
Did you run your sample program?
Did I run my program? Sorry.
So I was wondering if you showed us these 2 functions, right? Your greet function and the main function. Did you actually run that, or did I miss that?
Oh, okay. Let me see.
Which my question was, like, I take it would be interpreted, like, but also could you compile your AST into something that would run with like built-in Go? I mean, as long as you use the Go one roughly, then that should work, no?
So this approach that we are taking is to not interpret the program, but generate Go code. And so the program that we wrote after all the transformation is converted into this Go code. And so we could run this Go code, and it should just work like a normal Go code. Yeah. So for instance, the program was very simple. The only logic that is added is that when there was a printf, I added an import statement to the Go AST, so that it's a valid Go AST, because I want to use the format function package font.printf. So if I had implemented it in another way, maybe if I had used, I don't know, I could have used some other package and imported it as well. But we could run it as well, just to maybe we could run. Oops, not private. Yeah, I think so. Any other questions? Okay.
Is there any full languages which have actually been produced using this technique as of yet?
So this technique, producing Go ASTs, I haven't seen any. So I've looked at a few languages that are written in Go, but I might be wrong, but I looked at, there's a language called Go Plus, Go P, and it had forked the compiler as far as I could understand the code, and it wasn't generating normal Go AST. Yeah, I haven't seen any language that's using that. And I think there should be, because it's so good. I mean, producing Go AST is, we are all familiar with Go ASTs, and there are lots of tools for them. So why not use Go ASTs? I mean, why write compilers from scratch when we can use Go AST? And not just for running programs, but for working with the code as a data structure. I mean, AST is a data structure for representing code. So if we interpret our code, we won't have that. We will just execute everything line by line without knowing what's coming next, maybe, I don't know. So yeah, I hope that there will be some new languages, maybe.
Thank you.
Thank you. Okay, thank you very much for attending my talk.